So welcome to the UTIG Friday seminars. My name is Patrick Heimbach, and it's a great pleasure to welcome Dr. Spencer Jones from Texas A&M University, where he is an assistant professor. Just very briefly, Spencer has a master's degree in physics from University of Oxford, and then moved to the US to pursue PhD at the Scripps Institution of Oceanography with Paola Cesi, for those who know her. Working on the global overturning circulation, and then moved to the Lamont, the Earth Observatory, as a postdoc, and then also associate scientist. And then finally in 2023, started his position at Texas A&M. Spencer's focus is on, as the title also says, on trying to understand the mechanistics of the global overturning circulation, i.e. how is heat and traces being carried around in the global ocean. In terms of tools that Spencer uses, he's really spearheading or at the forefront of using Lagrangian particle methods to try to understand the water movements. And also for those who are using X-ray and these things, Spencer, I think, has been very deeply involved early on in the Pangeo project. So to the extent that X-ray now works as great, and you're able to use cloud native data sets, it's also probably partly thanks to Spencer's work behind the scenes at least. And so with that, yeah, please take it away.
Yeah, thank you very much for that nice introduction. Okay, you can hear me, right? Let me check with this on. Yes, okay, so yeah, I'm going to talk about Atlantic ocean heat transport, and particularly the roles of these three things: the AMOC, the Atlantic Meridional Overturning Circulation, the gyres, and tropical upwelling. And I know not all of you are oceany people, and so I'm going to try to at least make the first 10 minutes sort of some understandable thing that will help you to navigate the rest. So, right, this is a graph of global ocean heat transport, which is actually, this is taken from ECHO V4R2, but basically most products will give you a graph that looks very similar. So the black line is the global ocean heat transport, and that's right, the y-axis, and then this is versus latitude. So this is the northern hemisphere is over here, the southern hemisphere is over here. And the first thing to know about the global ocean heat transport is that in the northern hemisphere, it's positive, which means it's northward, right? And in the southern hemisphere, the heat transport is negative, which means southward. And this makes total sense, right? The sun is shining more intensely. We receive more sun near the equator, and so the ocean is transporting heat away from the equator. Great. But what we notice, right, is the blue line, which is, well, let's see whether I can get it. There we go. Okay, so the blue line, right, which is the Atlantic heat transport, is positive everywhere, and that means that heat is transported northward everywhere in the Atlantic Ocean. And if you know anything about this, it's in order to have northward heat transport by the ocean, well, you have to have warmer water flowing northward and colder water flowing southward, and that's what's causing this. And in fact, the Atlantic Meridional Overturning Circulation gives you that. So right, this is the stream function of the Atlantic Meridional Overturning Circulation, and the flow follows these contours in the red. It follows in a clockwise direction, so you have northward flow near the surface that's warm, and southward flow at depth that is cold. And so we generally think that the northward heat transport is because of the Atlantic Meridional Overturning Circulation. This is just like another view. So in equilibrium, the ocean heat uptake, you can just take the derivative of that ocean heat transport curve that I was showing before. And this is another paper that kind of shows this, but right, the ocean heat uptake is mostly happening near the equator. So this is the amount of heat taken up by the ocean, and it's positive near the equator, and then makes sense, right, based on what we said. In the North Atlantic, a lot of heat is being released from the ocean back into the atmosphere. So I just want you to have all of these things in your mind, because we're going to talk about the details of ocean heat transport, and it's good to be oriented. And the other thing to notice, right, is the Pacific is taking up a lot of heat at the equator. That's the cyan line. And then the Atlantic is taking up less heat at the equator, but it's still significant. When we think about what kinds of things could be transporting heat in the ocean, we might think about the gyres. This is a kind of classic figure showing the gyres. So right, there's the subpolar gyre, which is going counterclockwise. It's in the North Atlantic. And then we would have the subtropical gyre, which is here. Then there are some tropical gyres. And then there's another subtropical gyre in the Southern Hemisphere, which is counterclockwise. And so that's kind of the horizontal circulation of the ocean that happens in the top. Okay. I'm going to pause for a second. Okay, that's happening in the top 700 meters. We have this horizontal circulation. And then these are the subtropical cells. And these really just happen really close to the equator, within about 10 degrees of the equator. We have upwelling on the equator. And then we have wind-driven Ekman transport away from the equator. And then sinking of water that comes back and feeds that upwelling near the equator. So we're going to talk a lot about that in the second half of the talk. Okay, didn't go forwards. Oh, now it doesn't go forwards because I have to click here. Okay. Why do we care about this? Well, one reason why we care about Atlantic heat transport is that the Atlantic Meridional overturning circulation is bringing this some heat northward into the northern hemisphere. And if you were to have shutdown, and we can talk later at some stage about whether the AMOC might shut down. But if the AMOC were to shut down, we would have a reduction in temperature in the northern hemisphere, in the surface air temperature, in the sea surface temperature, and we would also have a change in precipitation near the equator, and that's because the intertropical convergence zone, the location of the intertropical convergence zone, which is this region of high precipitation, is set by the heat transport by the ocean. And so if you reduce the northward heat transport by the ocean, that whole band of precipitation moves, and that's why you get these kind of huge precipitation anomalies that happen when you shut down the AMOC. So these are just some kind of motivations for why we should care about this. And we don't actually know exactly how fast the AMOC is going to slow down or shut down, but based on the actual simulations that we have from CMIP6, we think that the size of the decline is going to be somewhere between 5% and 55%, which is huge, right? That's a huge range. But it also depends, it doesn't just depend on that range is not just dependent on the physics of the model, it's also dependent on how much CO2 we emit, right? So that's some of the variation. But yes, if you look at some of these models, some of them are shutting down or slowing down by 50% and others by much less, like this one only 12 to 30%. Yeah, there's a range. So yeah, a lot of the motivation comes from thinking about AMOC. But then I started to think, okay, well, it turns out that AMOC isn't like completely disconnected from the horizontal circulation of the ocean. And so I was really inspired by a little bit this paper, which is by Sarah Berglund. And she showed that in Nemo, 70% of the water that's flowing northward. So she looked at Lagrangian particles and she looked at how they get from the equator to the pole as part of the AMOC, right? So northward flowing near the surface. She found that 70% of the water parcels have to go around in this gyre in order to get dense enough to continue northward into the North Atlantic. And so this kind of shows that, right, that gyres are not completely separate. And it would be nice to kind of have some ways to understand which part of the circulation is doing which job. So perhaps some of these questions are a bit hubristic, but I wanted to identify what is the role of the gyres in moving heat northward at different timescales? Where does the heat come from that is being moved northward by the gyres? And where does the heat come from that's being move northward by the overturning, and what controls the strength and coherence of northward heat transport. And the truth is, like, I have not solved these problems, but I am trying to make progress in this question. And so, right, we're now at the stage where I can tell you what I'm going to talk about. So first, the first half of the talk is about a paper that has already come out, some work where we looked at heat transport and AMOC in the CSM large ensemble, and thought about different methods for separating heat transport by the overturning and heat transport by the gyres. And when this work came out, I kind of didn't feel that good about it. So I think that is kind of normal, but I do think particularly this work kind of fits into a larger story, and it doesn't necessarily make sense unless I tell you some other bits of the story. So I'll try to do that as well. And then the second half of the talk will be a little bit more like of a result that stands on its own. And this is about an idealized model. But first, yeah, I'm going to talk about heat transport and AMOC in CSM, these methods for separating, overturning, and the gyres, and looking at what kinds of results you get if you try to separate the heat transport by the AMOC and the heat transport by the gyres at some different latitudes. And then, yeah, I'll conclude. So I used the CSM large ensemble to look at heat transport, and this was work that I started right during this time when we were looking at X-array and trying to get it to do really big computations. And so, yeah, so we used this 40-member ensemble of fully coupled CSM1 simulations, which was on the cloud. I mean, I think it still is on the cloud. We had the simulations all have different initial conditions. So this is just a way to get the simulations to have different internal climate variability. And then I look at only the period 1940 to 2005, and I used Pangeo Cloud to work with this data. During this period, long-term trends in the AMOC are like heat transport are pretty small. It's really only in the future period that you start to see these trends in AMOC. And so I'm basically treating the ensemble like quite a long time series. Oceanographers tend to look at AMOC in density space, right? I showed you in depth space what AMOC looks like. This is just the same thing, but instead of depth being the y-axis, potential density is the y-axis. So light water is up here, dense water is down here. Northward flow near the surface looks like this. And you'll notice, right, at the equator, the northward flow is lighter. And then as you go over here, there's northward flow, but it tends to be denser because it's closer to the pole. And then we have southward flow that's in dense densities. And yeah, in this talk, the AMOC transport is defined to be the maximum stream function at each latitude in density space. And I'm going to look at 3 latitudes. I'm going to look at 5 south, 26 north, and 34 north. I was kind of motivated when I was thinking about this by the fact that I was sure that if we did not have any gyres, AMOC will follow the western boundary. And this is to do with conservation of potential vorticity. You don't have to understand that. You just have to know for sure. We know that if you had just had AMOC and no gyres, the AMOC flow would follow the western boundary on its way northward, right? This is the north. It would sink, and then it would flow southward along the western boundary as well. In reality, right, we have gyres, and so what the total situation is actually the sum of what's going on over here and the gyres. Now I'm going to talk about some different methods for separating the overturning and the gyres. Again, just to orient you, because of this thing called the gauge problem, any method we choose has to separate the flow into some different zero components where if you integrate the volume, you get 0. So an example of that would be if we just look at the heat transport through this orange region, right, which is this means into the page, right? So we have northward transport through this orange region, and heat transport through that region will depend on your choice of reference temperature. And so what this means is that if you say, okay, I'm going to measure my temperature in degrees C, you're going to get a different answer, right, from if you measure your temperature in Kelvin, because you're taking the velocity, you're multiplying it by the temperature, and most of what you actually see of that signal is not coming from the temperature anomaly, it's coming from the kind of mean temperature times the velocity. Whereas if we pick a region where the total volume flowing through that region is 0, then we don't have to worry about this, and we're good. So basically, we always should divide our flow into sections where the total transport through that piece is 0. And all of the following methods do that. So the most common method that people have used very much in the past is what I am now calling the mathematical method in Z-space. So it's a method, right, for finding the heat transport by the overturning, or for estimating the heat transport by the overturning. So we take, if these are the Americas, this is Europe, right, this is depth. We're going to integrate the velocity and the temperature at each depth level. And so, right, we're going to have a profile of velocity, we're going to have a profile of temperature, we're going to multiply them together, and then we're going to say, okay, that's the heat transport by the overturning. So because we've taken the zonal average, the average in longitude, that means we've removed the effect of the gyre. And so people historically have done that. They said the heat transport by the gyre equals the total heat transport minus the heat transport by the overturning, which they calculated this way. And this is like one of the reasons it's common is that if you have very sparse observations, there are some ways that you could calculate velocity that are extremely useful if you're just going to use this method. But in reality, flow doesn't follow depth surfaces in the ocean. Flow tends to follow more density surfaces. And so this method is perhaps not as accurate as we would like. And a good example for why that would be is if you have, right, for example, this flow is the northward western boundary current of the gyre. And then this is the southward flow of the gyre. So we have flow that's joined up in the north and that goes around. This flow, right, is higher up than this flow. And because of that, you're going to see it in this zonal average of the velocity. And so that will be counted as being overturning rather than flow from the gyre. This is another example, and this was the example that got me motivated to think about this. If you have heat transport, right, by the overturning and you really don't have any gyre, like I said, the overturning is going to be on the western boundary. And in general, if you have northward flow, I would imagine that flow is going to be warm because it's coming from the equator if we're in the northern hemisphere. And so this method is going to underestimate the amount of heat transport by the overturning, because this, right, in this situation, all of the heat transport is by the overturning. But because we took the zonal average of the temperature that we're using is not representative of the real temperature that's being moved. We could also do the same thing, but we could do it on density surfaces. This was often suggested to me when I started working on this problem, but it kind of has some similar issues to the previous method, although yes, flow does generally follow density surfaces. In an ideal world, we would see particles in a model and we would look at heat transport from a Lagrangian perspective. And this is hard work. And I think, you know, at the time when I did this work, I was saying, okay, maybe I want to come up with a method that solves this problem, so we can always avoid running particles. I think actually it turns out that didn't work. What the work shows, this is all spoilers, right? What the work really shows is you can use any of the 4 methods. They give you different results, and the results are not consistently very useful. And so you should probably run particles. Anyway, there are 2 other methods. This method is by Lintali. She's assuming that water is lighter in the western boundary current. So the water that's lighter in the western boundary current is part of the gyre. This makes sense, right? If you have heavier water, it's able to go further forward in the North Atlantic So go further north in the North Atlantic and feed North Atlantic deep water formation. And so she's saying the water that's going northward that's denser over here is going to go north and be part of AMOC, and the water that's lighter over here is going to come back in the gyre. And then I came up with this method, which was really based on this idea that I think AMOC's on the west, on the western boundary. And so I decided, okay, I'm going to make all of the flow that's on the western boundary be part of AMOC, and the stuff that's further east is going to come back round and be part of the gyre. And this was kind of based on this idea, right, that I had, which was the red line represents the AMOC. So you have flow of water that's kind of continuous all the way from the south to the north along the red contours. And then the blue is like the gyre. I'm not sure this is actually super representative of what happens, but this was what I was thinking when I came up with the method. So right, there are 4 different methods, and I tried them at 34 North, and you'll notice they all give you different numbers, which I think is really the main output of this work. It's that like all of us are going around saying, oh, we can separate these 2 things, and in fact, no matter what method you use, it's going to disagree with the other methods, and it's not clear which method is best in general. So the Z-space method gives you 91%. The density space method gives you that 115% of the heat transport is due to the overturning, right? Which actually means that you're attributing southward heat transport to the gyre in that case. The tally method gives it attributes 69% of heat transport to overturning, and the western boundary method attributes about 100% of heat transport to overturning. And then I tried again at 26 North, and the good news is they all kind of give you the same, they give a consistent answer with themselves, but that's not actually that helpful because we still don't know which one is best. So the good news is somebody else did some work, and Tooth et al. 2024 had vectored particles again in NEMO. And they seeded their Lagrangian particles in their model at 26 North, and they looked at where those water parcels went in their model. And they found that, so the red line, let's see, the red line is the heat transport by the AMOC, and the blue line, the yellow line is the heat transport by the gyre, and then the blue line is kind of other like eddies type stuff. So right, the red is the AMOC and the yellow is the gyre, and it turns out this breakdown suggests that the subtropical gyre is carrying 37% of heat transport at 26 North, which is most consistent with this method by Lin tally. And when they look at where their particles go, it is more consistent with the idea that, in fact, the water that's on the western boundary that's denser is continuing north and feeding deep water formation in the North Atlantic, and the water that's lighter, that's the water that turns around and comes back in the gyre. So yeah, the tally method makes sense here, but it's also true that, right, the tally method actually, she herself, who wrote the paper in 2003, kind of only applies it in these subtropical gyre situations. And so probably it's not a like general method where you can always find the heat transport by the gyre everywhere. It depends on what kind of, whether you're in the subpolar gyre, the subtropical gyre, or the tropical gyre. So at 5 South, it doesn't really make sense to use the tally method. And so I tried the other 3 methods, and again, they all disagree. The method that I came up with, the western boundary method, attributes 144% of heat transport to overturning. And it turns out that actually makes more sense at this latitude because, right, the equator, I should point with the thing. The equator is here, right? And so the warmest water is actually going to be here. And it makes sense that the gyre should transport heat southwards, because we think gyres transport heat from warm places to cold places. And so, yeah, this means this 144% means the AMOC is transporting heat northwards, and the gyre is compensating for that. The thing was, when I ended up using this at 5 South, I again was like, oh, now this isn't actually, it's more complicated than I thought. And that's because at 5 South, we have the subtropical cells, which, if you remember, right, that means we have Ekman transport that's southward at 5 South. And that creates this like little overturning that happens right here. That's kind of counterclockwise. And this overturning, it's not clear. Should we be counting it as the gyre? Should we be counting it as the overturning? I don't know. And so again, like, I think my realization is that all of this is just way more complicated than I thought it would be. And then people treat it when they sort of say, oh, we're just going to split the heat transport into one thing and another. So these are the conclusions from this part. All 4 methods give significantly different results. So which method you pick is important. And you should really be thinking about which method is the right one for you. In the North Atlantic subtropical gyre, it seems like the tally method is likely to be the best, because it really describes what the real water parcels are doing. And close to the equator, a lot of wind-driven transport is in the subtropical cells, and we need to do more work to understand how the subtropical cells, right, which are the vertical cells that are driven by wind near the surface, how that affects heat transport. And that's what the next part of the talk is about, but I'm just going to drink coffee. Okay. Oh yeah, and thank you very much to Scout Zhang, Ryan Abernathy, and Julius Busecki, who all helped with this talk. Scout was an undergrad researcher with me. Ryan was my postdoc advisor, and he really made it possible to have all this kind of cloud, data on the cloud, because in some ways, one of the bigger feats of doing this was it just involved a huge amount of data. We did a lot of breaking down the different variability, which I'm not presenting here, and looking at big data sets from the cloud. And then Julius wrote one of the tools that I ended up using to do this. So, okay, and then now I'm going to talk about a little bit of work that's led by Sanjana Satish, who is currently working with me. She's a master's student in India, at an institution in India, ISSCR Mohali. But she's visiting Texas A&M, and I've been supervising her to do this work. So we're trying to understand a little bit more about these subtropical cells that are close to the equator, and we're going to do that using an idealized model, and this is that model. So this, right, is latitude, this is longitude, and we have land around the outside, and then where it's red, we have ocean, and it's 4,000 meters deep. And then we have this kind of ridge near the center of the ocean, which represents the mid-Atlantic ridge. And so this whole basin is supposed to represent the Atlantic, right? And then this area is a reentrant channel, which is supposed to represent the Southern Ocean. And then we have sea surface temperature that looks like this. I mean, you know, this is what a sort of idealized version of sea surface temperature. To make our model do a kind of realistic overturning, semi-realistic overturning. And we also don't have any salt in this model. We wanted to keep it as simple as possible. We're really just asking questions about how does the wind impact the circulation near the equator, and how does that impact heat transport? And so, yeah, we changed the wind. This is the zonal wind stress. So that's right, the wind stress in the east-west direction versus latitude. And so we are just changing the wind really, really close to the equator, within 15 degrees north and south. And these are just some figures to kind of remind you what's happening close to the equator. We have wind that is usually in the westward direction, and that causes divergent Ekman transport, which causes upwelling close to the equator. And so, yeah, this is the actual expression that you would use to find the Ekman transport, which is the total amount of transport driven by the wind. And so you'll notice, right, the velocity, the transport is linearly dependent on the strength of the wind, and it's dependent on F, which we'll talk about in a second. But yeah, and we're going to change the wind quite a lot actually close to the equator. We're going to have a case where the wind is 0 at the equator, and we're going to have a case where we have really strong westward winds at the equator. Okay, I think that's everything. So yeah, we're going to change the winds close to the equator, and we're going to look at how does that affect heat transport in our idealized model. And so this is what heat transport looks like in our idealized model. So this is heat transport versus latitude. And you'll notice, right, this is supposed to represent the Atlantic. And in at least 2 out of 4 cases, the heat transport is northward at all latitudes, because this is positive. But right, in general, we have much more heat transport in the northern hemisphere, much more northward heat transport in the northern hemisphere, and less in the southern hemisphere. And the change in heat transport ends up being pretty asymmetric, even though we've changed our winds in a symmetric way. The change in heat transport is it goes much further north in the northern hemisphere than in the southern. Seconds, okay. Okay, and the heat transport also doesn't, this was actually a result, I didn't know that this was going to be the case. The heat transport doesn't change up here in the north. And so although the heat transport, the heat that comes from the equator gets moved from the equator all the way to 40 north, that's what's shown, right? We changed the heat uptake here by changing the winds, and that heat uptake gets moved all the way to here. That's what causes the differences in the different scenarios. There actually is no difference between our scenarios in the far north. And so the Atlantic Meridional overturning circulation doesn't care what the winds are at the equator. It's only kind of the surface circulation that it turns out cares. And so, yeah, stronger wind at the equator leads to more Ekman upwelling. This is just a graph that's showing the Ekman transport. So you actually get way big spike close to the equator, and that's because the Ekman transport is proportional to 1/f, right? And we know that F is going to be 0 at the equator. And that leads to a large Ekman divergence when you have westward winds at the equator. And so this figure is, so this one is just the overturning for the base case, which has 0 winds at the equator. It's the yellow case from before. Let's go back. It's this. So the base case is the yellow case with the least wind stress at the equator. And you can see, right, we have depth, we have latitude, we have this kind of overturning, and you'll notice, right, this axis is just from 0 to 4,000. And then we've zoomed in a bit because it turns out when you change the winds at the equator, it really only affects actually the top 400 meters, but we want to show you a little bit more. So to prove to you that there's not very much going on down here. So when we change the winds at the equator, right, we have more upwelling close to the equator, more divergent flow away from the equator at the surface. And so we get this strengthening of these little cells, the subtropical cells close to the equator. And so that is great, but it's also very concentrated very close to the equator. And already I'm like thinking, this is weird because I just showed you this figure, which shows you that when I change the winds, the heat flux, even at kind of 30 degrees north, is really different between the different cases. But now I'm showing you that the circulation actually really isn't very different between the cases. The circulation change is really just being changed really where the wind is changed. And then we plotted these things in density space, and it's okay if you find reading these hard. I find reading these hard, and I look at them all the time. So basically, right, this is the circulation, this is density, this is latitude, right? And the AMOC is the red cell. And what we're looking at is how much does this change? And particularly sort of, you don't actually really see very much change in the cell, this like deeper red portion, but you see a big change in this red portion right here, which is associated with lighter waters. So as we increase the wind stress, we end up with more of this kind of lighter cell that's bringing warmer water northward and colder water southward. And And so, yeah, so in density space, yeah, it seems like the Ekman upwelling is impacting what we see over a wide range of latitudes, but not north of this blue line, which is 40 north. So why does it not? Why is 40 north the limit? Well, we think it's because 40 north is where the subtropical gyre ends. So we can have warm water that upwells here at the equator, and it can feed northward flow on the western boundary. And I'll show you another figure of this in a second. It can flow northward. This warmer water can flow northward on the western boundary and continue to bring heat northward. But this warm water is too light. It cannot get past 40 north. This water at the surface is very cold. And so this water that's light and that's going northward, it has to reach the surface, get colder, and come back. And so that the subtropical gyre can move this heat that we got from the equator northward, but it can't reach the North Atlantic. This is like my first effort at a 3D diagram of what's going on. So you can see, right, the yellow bit is supposed to be these subtropical cells. So we have upwelling at the equator, and then they go, they're kind of limited in latitude to only within a few degrees of the equator, maybe like 10 or 20 degrees of the equator. And that upwelled water, which is shown in the orange, then is going northward. It's going to the western boundary, and it's feeding the western boundary current of the subtropical gyre, right, which is also going northward. And then at some stage, it gets to a latitude where it's like the lightest water out there, and it has to be exposed to the atmosphere and get colder. And so it does that. It gets exposed to the atmosphere, it gets colder, and then it comes back around and sinks and comes back and goes quite a convoluted path. But eventually it comes back to the place where these subtropical cells are, and it upwells again. And we think that's why we see this kind of heat transport that we're seeing. It turns out somebody else was also thinking about this, and no surprise, it was my PhD advisor, because you tend to think in the same direction as your PhD advisor. But this is, she did not do, Rousselet and Chessy did not do all of this, but they did notice that, in fact, they have water parcels that they've run in a very idealized model, and they are doing this kind of loop where you have upwelling close to the equator. Then they go into the western boundary current of the subtropical gyre. They kind of go up to the surface. They get colder because they're exposed to cold water, to cold air at the surface. And then they sink and they come back round and come through. Now, I know this figure is not necessarily interpretable unless you've already seen the previous one, but once I realized, oh, I think this is what's going on, I was like, oh, I read something about this before. So I went and looked at it. Okay, I'm going to finish early, which is fine. So we found that in our idealized model, changes in wind close to the equator have an impact on heat transport by the subtropical gyres, but only a very small impact on heat transport in the far North Atlantic. And so they really don't have an impact on North Atlantic deep water formation. Okay, it was short, but that is the talk. Thank you very much. Thank
you very much for an excellent presentation, and we have time for questions.
Who's first?
I'm so sorry. I'm used to just being at a desk. Thanks so much, Spencer. That was such a great talk. I wanted to ask first actually about the last piece of work. So firstly, I think your master's work is super relevant here. So when you see that the change in the overturning circulation is restricted to just the vicinity of where your wind perturbations are, I think that's because from your work with David, the wind change is either going to drive an overturning change by just projecting onto causing local Ekman changes, or projecting onto an overturning, external mode of overturning circulation. So just changing the barotropic flow really locally. But what I wanted to ask is that if you'd included salt changes in your idealized model, then do you think that the water that was being advected further northwards by those invigorated tropical cells would eventually have increased the density at high northern latitudes, feedback on a change in subpolar North Atlantic overturning, and then eventually invigorate the meridional heat transport at high northern latitudes?
Great question. And I think you're like just saying, oh, we should write a proposal about that. But yes, I would expect that if you have salt, there would be some different effects happening because, right, the water that reaches the surface and comes back probably is actually not exactly the same water every time, and some of the water actually ends up continuing and bringing salt northward. I don't know whether that's a coherent thought. Basically, right, like if you have different properties at this location, if it's temperature, it doesn't matter because that's exposed to the atmosphere. But if you have salt, right, that does matter because it is not actually, I mean, it is affected by precipitation, but it's not, its absolute value is not returned to some value. So yeah, I think you're right that probably there are some interesting questions here. Yes.
Yeah, it could be a long time scale, but I think you would see a meridional heat transport change if you had a salt anomaly that could be advected further. Yeah. Thank you.
Sorry. I actually had the same question about the what if you had salt, but I have another question, and I'm not an oceanographer. So here's the very basic question about the first part about the diagnostics of AMOC, northward heat transport, which is, what if you just looked in between the gyres? Like, why are people just like, okay, you want to know northward heat transport. What if you just looked in between the gyres and then you could know, like, okay, if you have two numbers, probably the northward heat transport in the gyre is somewhere in between those two numbers, right? Like,
yeah, you are asking actually a really good question, and certainly, like, I think in an idealized model it's possible to do that, and I think that is a thing that I'm actually trying to use a little bit in this second piece of work. But one of the problems is in a realistic model, like there isn't like a very clear latitude where the gyres end. So you could do that, but you probably are going to get something that kind of includes some of one gyre or some of another gyre. And sometimes you get like both actually included if you just take a constant latitude slice across. So yeah, it turns out it's a little harder than what you think.
Hi, thank you for your great talk. I was wondering about, so I'm not super clear about what should the role of the Arctic Ocean be in my conceptual view of because, you know, we observationists doing Arctic observations, we was like, oh, this is super important for the global climate. And then you have a climate modeler in a room full of observationists like, yeah, you know, the Arctic is like this useless little limb that's there. If we ignore that, we're fine, right? He could be happy he was online in that presentation. But what's your feeling, is it rather, I guess, about how important is the Arctic? Can we just ignore it or should we go back?
That's a very leading question, but okay. I think that, right, one of the things is that motivated me particularly in the second piece of work is the Atlantic multidecadal variability, which is a thing that we don't even know whether it really exists. But right, I feel like understanding how all of the pieces fit together involves understanding sea ice, and probably the Arctic actually is quite important there. But it's true that like one of the issues that is actually, and some people here are very aware of this, it's really hard to model the Arctic. We don't have good observations. And so it's easy for us to say, oh, we don't need to worry about it, right? Because if you're an observationist, you have to be able to persuade people. No, if you're a modeler, you have to be able to persuade people, oh, you should trust my model, even though the temperature in the Arctic is completely wrong. That's kind of a normal thing to be saying. So yeah, I think these things all interact, particularly, right, the wind at the equator does seem likely to be connected by teleconnections to processes that happen very remotely. And so yes, I think it's relevant. But also, yeah, I perhaps can't say exactly related to this work in any more detail.
Yeah.
Okay, we're gonna have some more.
Oh my.
Okay, this has been.
I think that's why Austin doesn't have a football team, no? We can audition for it. Actually, I think this is a great idea for another proposal writing, I think, because I had always wanted to run a model where we simply close off the Fram Strait, the Bering Strait, and the Canadian archipelago, and see what kind of circulation it would entail, you know, because good, we should really ponder about this. And then I have a quick question, actually. I had thought you also done the tracer, no, not tracer, the Lagrangian in the MIT GCM, similar to what the people were doing for the NEMO, or no?
No, the answer is no, I did not do that. I think it would be nice to do that. And I did spend some time trying to do it, but it turned out like the size of the big data problem that I had. So right, this work was in CSM. So I spent a lot of time dealing with the big data problem and not running particles. So yeah, that was like I began that project, but we didn't do it.
Another proposal as well, because we did run the trace and we did run the Lagrangian.
Yeah.
Sorry, who's next? That's easy.
Thank you, Spencer. I am wondering about variability in the meridional overturning and variability in the gyre. And I don't fully understand how they're connected. And so I was just wondering if you could share a little bit about, do we expect variability between those two modes of heat transport to be correlated? Do they vary on different timescales? Are there different mechanisms? Yeah.
Thank you. Great question. In fact, I might even have like, okay, let's see if I can do I definitely have a skip slide if I can get out of it that shows this or something relevant. Is it here? It's one of these, I think. Maybe I deleted it. I deleted it. Or maybe it's the blank one. Okay, never mind. So yeah, the answer is, I'm just gonna go back. The answer is wind stress, right? Wind stress driven variability, which is generally, we think the gyres are driven by wind, right? Tends to be shorter time scale than AMOC. But it turns out that there is certainly some interaction, partly via this mechanism that Helen was talking about, right? That the gyre is moving heat and salt around, and how much heat and salt makes it to the North Atlantic is hugely important for the strength of Atlantic Meridional overturning circulation. And this is kind of like, you're actually asking, like, one of the questions that was motivating me when I was trying to do this was, I was like, wouldn't it be great if we could like come up with a method to actually understand this? And I think the answer is just like, you probably just have to run particles, but like, we just can't go around that. Yeah, like it does seem like that variability that you see. And in fact, there's some work by Sarah Larson who shows that if you turn off the wind-driven variability, so you run a climate model and you sort of make the wind cycle that the ocean experiences be the same annual cycle every year, right? That would lead to very, very different AMOC variability. So it's clear that the gyre is having some impact on the kind of longer term variability. But yeah, it's all not very well understood.
Okay, cool. And can I just ask one follow-up? Because I know you've thought about the last glacial maximum too.
Yeah.
So just like broadly, do you expect the sort of role of the gyre to be different during the last glacial maximum because of the changes in boundary conditions? Or is that not known, or is it really the same?
I suspect that the role of the gyres is pretty similar at the last glacial maximum, just because, right? I mean, first, we don't know what the AMOC did at the last glacial maximum, but if, as some people say, it shoaled, right? That all happens at deeper depths than where the gyre is. So probably what's happening near the surface is pretty similar. Having said that, right, we have very limited information, so it's very hard to know what these things were like, particularly, right, like it's easier to understand the largest scale transport from proxies than this kind of stuff that happens in the gyre. And yeah, I would not recommend spending lots of time on this question.
But if it was windier.
Can I ask a sort of a follow-on question, which I had anyways? Perturbation of the wind, you looked at, focused on the equator, right? So if you look at the mid-latitudes, and maybe related to the last glacier maximum, maybe the jet stream may have shifted much more equatorwards because of the presence of the Laurentide ice sheet. And in contrary, right, so we expect maybe the mid-latitude westerlies to also shift a bit polewards under climate change. Is that something that you have looked at, or can you speculate how you think the results would?
Okay, I like that. That is a huge question.
Or proposal?
I think, yeah, the answer is at least right in the, let me go to a place where we have the heat transport. Right, in my idealized case, if you move, right, the latitude of the westerlies, that's very much going to move how far north the heat gets to. But I don't know that it's necessarily going to impact. I think you would have to do a bunch of realistic geometry simulations to really get at how would that impact the transport of heat all the way to the far north, because it's likely to be pretty geometry dependent, how much heat gets across that boundary between the subtropical gyre and the subpolar gyre, I would think. I don't know whether I have anything else, but yeah, I think the truth is it's probably going to have a big impact on yeah, where the heat gets to. So that could like, right, if what you care about is the temperature in Europe, right, that's probably huge, but it just depends on what you care about. If you care about global climate, it might be less important.
But following up on this, I mean, it looks like north of 40 North, there is no change in the heat transport carried by the ocean. So how would what would be the impact on heat to Europe, let's say Northern Europe?
Well, so I guess what I'm saying is what matters is if the westerlies, right, you're talking about, okay, let me make sure I understand what you're talking about. You're talking about, maybe I'm not answering the right question. You're talking about these winds, right, the westerlies.
Well, actually, now I'm sticking with even this experiment and looking at the heat transport carried by the ocean based on your perturbation experiments. Okay. Actually, I'm switching back to what you've actually done,
okay.
And as opposed to let's stick to what we were talking about, discussing the mid-latitude westerly shift. Indeed, right? So you would see an extension of the transport towards the northern latitudes, and that
exactly.
would
That's what I'm saying, right? If you move this northward, then more heat is going to get end up.
Yeah, no, that's good. That's good.
You can ask a new question if you want to. Yeah, just like
Thanks. This is a really remedial oceanography question. Does AMOC always, or AMOC type things fundamentally always go south to north, or could you arrange it an ocean to go the other direction?
Yeah, that is a great question, and the answer is we are pretty sure that AMOC goes in the direction that it does because of the position of the reentrant channel.
Okay.
Right. So the fact that there's latitudes with no land in the Southern Ocean means that we have northward flow near the surface and southward flow at depths. But if you had your channel at the other end of the Earth, or if you had multiple channels, the situation would be very different. And I think the reality is there are people looking into this kind of question, but it's really very like a planetary question, right? It's not an oceanography question. I mean, perhaps, yeah, very paleo topic as well. Yeah. Okay. Any other questions?
As an atmospheric scientist, when you're looking at wind changes, my brain goes to emissions. And so greenhouse gases or changes in aerosols, which are very uncertain in the future. I guess like at a high level, conceptually, how big of a role do you think the future uncertainty in emissions affects the wind-driven changes you're looking at? Or how much of this can you know to be true given that future uncertainty in those wind-driven changes?
Okay, great question. I think the answer is I spend a lot of my life thinking about why is the mean ocean circulation like how it is, and I spend a limited amount of my life thinking about what the future circulation will be like. And so the truth is I don't know what the expectation is for these winds. I do know that if you look at historical time series, the winds are, let's see, where did the pointer go? Oh, maybe it's my fault. Oh, maybe I'm just pressing the wrong button. Yes, that's right. Okay. Yeah, so the red is probably closest to what we have right now in terms of winds, and there's not very much interannual variability at the moment. If you look at time series since 1980, it's very much like the equatorial winds are pretty similar. And so yeah, it's possible that there might be really long time scale change, but I don't think it's like they're going to change that imminently, just based on what the current time series looks like.
Thank you.
I wanted to follow up on Duncan's question, actually. So how important to keep driving things in the way they're driven now is the depth of the Southern Ocean through time?
Okay.
I mean, it seems like you need that gateway, right? But does that gateway have to be full ocean depth?
Okay, so the answer is the depth of this cell, the Atlantic Meridional Overturning Circulation cell, is
Kilometer or less.
Yeah, but it's really set by the slope of surfaces of constant density, isopycnals, right in this channel, and the slope of those surfaces and all of the circulation that comes along them is kind of enabled by the fact that the channel is open. And so I suspect if you have like a 500-meter depth channel, it's not going to be sufficient to give you this kind of AMOC situation. Although it probably wouldn't be, I'm trying to think on the fly about what it would really be like. Yeah, I would anticipate that probably you wouldn't end up with such a deep AMOC in that situation. But I think you're asking a hard question, and I probably need to think about it more if you want like a certain answer.
Thanks.
Hi, I'm Francesca Samsel. I'm actually over at TAC, and I am going to go on record saying I'm the least qualified person in this room to ask a question. Let's just be clear about that. But I spent 10 years working with ocean scientists at LANL modeling three-dimensional ocean transport and Lagrangian models and all the, everything. We did it all. And my brain still hurts from that. But so what I'm trying to do is I'm trying to understand, and this is where the naivete of my question comes in. I'm trying to understand the role of understanding the gyres in isolation, because we did a lot of work where we're trying to understand how everything impacts everything else, because everything does impact everything else, and the role of the depth was a focus. So I'm just trying to understand how this fits in to our broader understanding.
I think that what this is about is okay, like I don't know.
I'm sorry. I'm sorry.
No, I think it's a good question. It's just like it's definitely a question that nobody's ever asked me before.
That's my specialty.
So I think that how does this fit in? Well, there are some pieces that are mostly about variability, that are about like, okay, we want to understand what's the role of these different pieces, and that's because if you want to understand, I mean, I guess like if what you care about is a model and you want to understand, okay, why does this not look like the real world? Understanding how the wind impacts this thing, or how the gyre impacts heat transport, allows you to then sort of trace back what's going on without having to run an adjoint model, which you could do if you had an adjoint model, right? But if you don't have that, right, you're going to have some logical chain. You're going to say, okay, my North Atlantic is too warm. Is it because the gyre is too strong? I noticed that the gyre is too strong. So you can sort of do some, it helps you to understand the connections to be able to split it down into these pieces, maybe.
And just as a follow-up, do you run ensembles to compare and determine?
So I don't run ensembles. That I work at a university and it's too expensive for me to run ensembles. But I have been looking at ensembles that are run, right, like in other places. But yeah, in general, I am not running ensembles.
Would that be helpful to you?
No,
it's a good answer.
I think the answer is no, but that's to do with the fact that I care about, what I'm interested in is how the ocean works, right? And that's not the same as being an expert in prediction, right? And yeah, and that's what you really need to spend your time doing ensembles for. Thank you so much. Thank you for